Okay, welcome back. So we have, I don't know where this is from, but a positive integer n is consistent if 2 to the x, so powers of 2 to the n plus x and, like, 2 to the n plus x and 5 to the x always start with the same digit when they do have the same digit. Okay, what is this? What? Okay, sure. And it says compute the product. I'm probably just going to compute them all. I can't imagine that it's indirect. Um, okay, so I should multiply them together, right? uh, like, you know, there's a 2 and a 5. Of course we're going to multiply them together. So this is 2 to the n times 10 to the x. So, okay. If two numbers, all right. Wait. I was going to say, it would be really funny if, for some reason, it was hard to determine whether n equals 1 was consistent, because then the product extraction actually helps you. You don't have to figure it out. But that can't be true, right? So, 2 to the x plus 1... Having the same, it's they, if they have the same leftmost digit, like, then that digit is equal to a particular y, right? Or something like that? I don't know. It's a, yeah. Um, n plus 1, n plus 1, 5, 5, 5. Should I just make a table of powers of 2s and... I'm going to write some powers of 2s and 5s up. We can practice my arithmetic skills. Alright. Okay, bang. 1, 5, 25, 125, 6, 3, 1, 2, 5. 15, 6, 2, 5, 7, 8, 1, 2, 5, 3, 9, 0, 6, 2, 5. But, like, okay, what does it mean if you have two numbers that, and you know their product, can you say what their first digits are or something? Florida online. I see. Florida. All right, cool. 36, 1, 2, 5. This is a statement about log. It's a little, I don't know. But, like, okay, suppose I told you that two numbers had product, like, I don't know, 1024 times the power of 10. The first digit has to be 3, right? Like, it just has to be 3. Or, okay, it could be 1 as well. That is also possible. But I wonder if there's certain numbers for... Because the n is actually fixed, right? That part doesn't vary. So if I told you a number is, like, if two numbers have product, like, 2 times the power of 10, and... Well, it's a little hard to say, actually. No, that's not quite correct. Take a large power of 4 that is very close to a power of 10. Okay, so like suppose like n is 10 or something, right? Or even if like n is 0, actually. I think even n is 0 is interesting. If two numbers have product equal to a power of 10, what can you say about the first digits? Because okay, there's this thing where like here. What am I trying to say? So if you have numbers that whose first digit is 1 and I multiply them together, the product, the first digit ought to be somewhere between like 1 and 4, right? Something like this. Let me write proper notation. So this case is pretty bad because they differ a lot, but their other cases are not really so bad. Okay, let me just write them all. So if I have like 2 and 2, the first is like statements like of this shape are true. Like if I take two numbers whose first digits are both 3, their first digits of their product should be between like, it's either 9 or 1 actually. There's no other. And in fact, you can say like, I don't know where I'm going with this. Has to be 3. That might be correct. I'm gonna finish writing this table because I want to see what the entries are. But first digit, it's not even first digit of the, it's like I want to talk about the first 2 digits of the product. How about that? I'm gonna zero pad the product because I can. We're not looking at the first digits of the final product. So I'm gonna zero pad them, and this will tell me what like the first couple digits of the zero padded product should look like. 5, 6, 7, 8. The right hand side should all be strict actually. So this should be pretty good, right? Because I don't know. Suppose n equals 6. Okay, suppose n equals 6. If you have two numbers whose first digits both coincide and their product starts with reads 6400000, then yeah, yeah, revealing that it's a finite set gives away a lot. I agree. I was very surprised when I first saw that it was supposed to come out to a finite number. But yeah, like 64 will be a good one because your in multiples of no, I don't think it's multiples of 3. N equals 6 will work though because it tells you that if you have two numbers whose product is 64000, their first digits are unambiguously have to be 7, right? So this is good enough to tell you that n equals, so 1 doesn't really count, but n equals 2. Wait, is it 2 for? Hang on. Okay, actually it's a little murky. But n equals, I think n equals 4 should definitely be okay. If you start with 1, 6, can you get there? No, you could get there. Wait, hang on. Now I'm confused again. Hang on. What? What is going on? I guess I need to care about the number of strictly less than 64. Yeah. Strictly less than 64. Damn it. If it starts with 6-4, it could be like two numbers whose first digit was 2 or something like that. Right. Damn. N equals 4 work. Well, right now I'm not using like the digits of, like right now I'm only using the product on the right hand side and trying to read things off of that product, which might be why I'm running into problems. It just feels like there's two possibilities for everything for some reason. Depending on whether the number of things in the like dotted bit is, no, it can't be right. Do I like care about the parity of X? Wait, does n equals 2 actually work? I have a hard time believing that, actually. No way, right? Start with 2 requires 2. Okay, why is it bad if they both start with 2s? Or Yeah, 2 squared is 4. So, like, yeah, that's what I'm running into. Like, I feel like if your product is 2, 4, 6, I would believe that, honestly. I just... Why is it not okay... If you have two numbers whose product is 4 times the power of 10, why does that... How do you show that it's like you don't have both 2 and 6? Or start with 2 requires both 2, 2, 2. Like, can they not start with 2? If the... Oh, that. Okay, yes, I agree. Yes, very good. Yeah, they don't happen to be 2 times 10. Right, it's not just that it starts with 4, it's literally 4 and then all zeros after that. Oh, okay. Alright, fine. Yeah. Okay, I agree, and that... n equals 0. Well, it said positive, so screw it. Okay. And then to show all the other numbers fail, do I just do some sort of density argument, right? Or like the starting digits of 5 to the x can be pretty much anything is the theorem. Oh, I really don't want to formalize this. Oh no. But like, why does n equals 8 fail? It's because 256. You know, you can find you look at the table and look for what counterexamples you want. So on the one hand, there's 2.5, and then on the other hand, there's you know, it's like 2.56 and 25.6, and you're like, okay, I should be able to cook up a power of 5 whose first digit is 1600000, and I should be able to cook up a power of 5 whose first digit is like, you know, whatever it is, like whatever 5 square root thingy is. Yeah, log 5 is irrational. Writing it up is not fun. Can I just not write it up? So the reason this didn't work is because for yeah, you need to be a little over. Yeah, okay. Yeah, babe. Yeah. Yeah, I know 246 is definitely answer. So yeah. I think we would have gotten it eventually as well. No, I feel like, cause I feel like what the kicker was, we were like, oh look, 4, 16, and 64 are actually like show up. Like, I don't think we would get hung up on n equals 8, because as soon as you try n equals 8, you're just like, lol, no, that you can't do the same thing, right? Because 25.6 is not. No, I don't think we would have. I don't think anyone seriously at any point thought that n equals 8 would work. N equals. There was some talk about like multiples of 3 at some point, I think, but I don't know. I don't think that felt right. Okay, yeah, but for the Otis version, we're definitely writing up. We're definitely taking out the answer extraction. See, if you wanted to put this on a short answer contest, you're supposed to say find the sum of all consistent numbers less than 2023. And then people can't tell it's funny. And then they get mad at you and they find out there's only finitely many. Where in Otis is this going? Miscellaneous. I think this is Miss NT. You could maybe argue its size, but I feel like digits are just so ad hoc that it's just like, no, it's just free for all. No, we're not putting this in dummy. Okay, we said this, so I don't. How do I cite this? Do I just cite this as Florida 2023 or something? Florida. Alright, sure. Oh geez, it's almost... Okay, so everyone that's still up is either up too late or is on the West Coast. From the US. Okay, you know what? We say a pair of positive integers nd is great if 1 less than d less than 10, and whenever 2 to the x plus n and 5 to the x have the same leading digit. Actually, we don't even need this. Is if the following... I'm just being a troll at this point. Statement holds. You have to be... if x is a positive integer for which have the same first digit, that digit is equal to d. In particular, d less than 10. Find all pairs of positive integers nd such that the following statement holds. Much better, you see? Okay, so that means I actually have to figure out what they were at. 2, 6, 4, 16. What did we agree for 16? It was 1. Yeah, okay. And 6, 64, so I want the 6.4, 2. This is an amusing problem. To show these work, we start with the following wonderful when one multiplies two numbers with this. Hence, if two numbers have product, first note that 2 to the x plus n times 5 to the x. the same. They must have that leading digit is 2 or 6. Moreover, the former case can only occur if the two numbers are exactly of the form 2 times 0. So in the situation of the problem, if 2 times x plus n leading digit, that leading digit must be exactly 6. In the same way, character development. There's 4, 1, 6, 2, 8, the same way. The converse is painful. It relies on the following lemma. For any finite string in decimal digits, some power of 5, not j about 2016-6, with that string of digits. Omitted, but essentially follows. Well, okay. It's irrational, and hence there exists, for any epsilon greater than 0, there exists e such that the fractional part of e log 5 equals log 5 to the e. Also, Otis is base e, so I better use an integer. I'll use k. Is between 0 and epsilon. Which implies for any epsilon greater than 0 and real number r, r plus epsilon. Okay, hence, for any interval I which is contained in 0, 1, non-trivial lies in I. Okay, and then do work. Kronecker approximation. I'll include the name. Yeah, I know what you mean about it shouldn't have a name because it's so easy to prove by hand. It's like Reims theorem. Everyone freaks out the first few times they see it until they realize it's like, oh, 3 angle chase, and they're like, wait, why does this have a name? And it's like, it has a name so that you know it's that exact 3 angle chase every time you see it. But there's nothing happening. Rainey's theorem. That is something different. That is a little more substantial. Now we need to do some work. Explicitly, if 2 to the n is not a 2-digit perfect square, there are two entries in the table that could give to the earlier, for which the first two digits line up with Tuesday. Wow, someone saved up for an ad break. Then use Kronecker approximation to rig 5 to the x such that it starts with some integer s, for which s squared is equal. Okay, well, we'll give these digits names d1, d2,